Hey everybody, how's it going? Welcome to the seventh lecture from Data Science for Econometrics. We're going to jump right into it today. So the first thing I wanted to point out is now is a time, and I will send information about this in the Canvas page, but I want to start this lecture talking about the project. So recently, we've touched on three main areas that sort of separate econometrics from other aspects of data science. One of those things was generalized least squares, which are models where we're trying to adjust for violations of some of the assumptions of ordinary least squares. The main two we focused on are heteroscedasticity and autocorrelation. Those could appear separately or in the same data. And so that is one area that you could focus your project on. You could say, I believe there is heteroscedasticity and or autocorrelation in some type of data set, and I'm going to do my project around that idea. So that could be something like estimate it with regular OLS, show evidence that you have either heteroscedasticity and or autocorrelation, and then adjust your estimation to try to account for that. And you've already seen some methods for the project we'd want to push a little bit more. But in general, you could imagine sort of extending one of your collab assignments into your project. The other area that we touched on last time was endogeneity and instrumental variable estimation. That would be another area that differentiates econometrics and would be a great area for a project. So that could be either, look, I have a research question where I collect data and plan on running a regression, but probably there's some type of endogeneity issue in this data. Remember, I gave you a list in this collab notebook and in the video, I provided a list of all of the different sources of endogeneity. So there are many. So there's definitely a lot of different projects that might involve fixing regressions for endogeneity using something like instrumental variables or two-stage least squares. Now, particularly in this area, and maybe the next one too, because the next one that we're going to cover today, treatment effects, also basically aligns with a lot of things like endogeneity. I am okay. This one, I think a simulation would be too basic, maybe, unless you could convince me. Like, there's definitely very complicated problems here that you could come up with. These ones are basically complicated off the bat, and I am okay with you guys in general. And I think this is a better example of where you might do this. You could say, okay, I'm going to come up with a system or story about endogeneity, kind of like supply and demand. One student's already thinking about predator prey. And then either I'm going to go collect data on quantities and prices in the one case, or predator and prey population densities potentially in the other case. And then I'm going to show, like, I'm going to argue this probably has a simultaneity or endogeneity issue, and then present the results of a regular OLS regression, and then present the results of a some type of technique, whether it's instrumental variables, two-stage least squares, or something else. Or another interesting way to do it, and will align with the homework you currently or you just finished, is simulating data. So you could simulate this problem, show that it's an issue, and then simulate the solution for the problem. There's trade-offs there, obviously. So in simulations, the benefits are like we know the truth because we coded it into the simulation, and then we can compare our different estimation results to the truth and build a really long, strong, clear story about endogeneity. The cost, of course, is that you're not dealing with real data, so you might be informing the use of how people need to think about real data in those contexts, but you're not using it. Of course, the other way to go would be to actually collect data, as I mentioned a second ago. You kind of assume, but theoretically argue that you would have an endogeneity problem, because that's what we did with supply and demand, right? We did a simulation, but before that, we theoretically argued that if both of the curves were shifting around, then you wouldn't be able to just collect data on prices and quantities. So if you're going to collect real data, which I think is a great thing, then that involves coming up with a theoretical argument about why you have an endogeneity problem. Now, if you want to go really hard, you could combine a simple simulation showing an endogeneity problem. Then you say, okay, now we've seen through this simulation that this could be a problem in this system. Now I'm going to collect data and I'm going to show you, assuming that we have that problem that I explained with the simulation, and then we're going to apply the solution to the data. Now, that's a little bit harder, but so kind of the way I want to think about it, I could do a simulation or collect observational data. If I'm going to do one of those, I want to go kind of deep, but if I'm going to do both of them, I can do a little bit less on each side. So I feel like that's, in terms of like getting to the end of a project, that's a trade-off I'm okay with you guys thinking about. Now, today we're going to talk about treatment effect regressions. But before that, I was going to show you an example of what a poster from last semester looked like. Now, this isn't necessarily, this is a great project. This is a simulation version, and this is actually based on the homework you guys were just working on. So this student set up a system of equations based on a story about housing. So they're like, look, housing prices probably depend on demand, sales, and also probably depend on the cost of producing a house. In turn, the cost of producing a house probably depends on the cost of materials and the cost on labor. And then the thing that makes this system interesting is those labor costs in these construction costs turn around and they again depend on housing price. So this student argues rigorously that if you tried to just estimate this equation, you would get biasness in beta 3 and beta 2 estimates because of the simultaneity endogeneity issue that lives in this system. Then this student does the simulation version. So what's nice about that is that they code in the true parameters, show that those estimates are biased. Notice that this is a 1 is not in the confidence interval, 0.5 is not in this confidence interval. So they're showing the biasness of OLS. And then here you go, you have basically right on the border here. So it's not completely fixing the problem, but better estimates from two-stage least squares. And then here, although the endogeneity problem exists on the construction cost variable, the student shows down here that through what's called smearing, this endogeneity problem on construction costs also leads us to the wrong estimates of beta 2, even though that's on a assumed exogenous variable. So I'm showing you this. This is how you might do a simulation version, but more so I'm showing you sort of the size that's expected of the poster presentation. So I don't really want to upload this because I'm worried too many projects will look too much like this project if I upload this. So really I'm showing this you this based on the size of the project, how much content is necessary, and one potential way you could go about it. But I really want you to focus on what is of interest to you. Now, and it's okay for you to deviate. I think these are sort of the main three things I see: somebody working with generalized least squares, somebody working with two-stage least squares or instrumental variables, or somebody focusing on a treatment effect problem, which has a lot of the same issues as we'll discuss today. Now, I am okay with you deviating from any of those. If you are, though, I think you should talk to me sooner and more so we can discuss really making sure that your project aligns with the things that we're learning in this course. You might be like, I hate all this. I only care about like algorithmic machine learning. I'm sorry if that's true, but I do want you to do a project that aligns with this course to some degree. There are ways to implement some of the things we've talked about in this course in more machine learning type contexts, or use machine learning to solve some of these issues. Those can be a little bit more complicated. If you have ideas about that, I think that would be great. We should just talk about it sooner than later. Okay. And I will update some of I'll send you an announcement sort of summarizing what I've said here today. And the main thing in the short run is that you have abstract submission. That's in about a month. You do not need to be done by any means with your project by that date. Really, you should be thinking more about poster printing. So you'll have only about 10 days between abstract submission and poster printing. You have to pay attention to poster printing because they'll print our posters, like they have deadlines. because tons of students are trying to print posters at this time period. So you should be aiming for having something relatively complete by this date, because that's when you're going to have your final poster. There's a little bit of flexibility about that, but we really want to be on it. Now, in terms of that, you are getting a break from your collab assignments. So notice treatment apart effects part one, there is no collab assignment in this module. So you have some time before the next assignment. So definitely take that time to start brainstorming, thinking, meeting with me about your project. Okay, let's get into our treatment effects part one collab. That video isn't there yet as I speak because I'm making it right now. So treatment effects are, the definition is the causal effect of usually a binary categorical regressor on an outcome. Now we can loosen that binary categorical regressor on thing, but we motivate almost always this conversation assuming that it's a 0-1 thing. So on an outcome, so a dependent variable, so we're interested in some outcome, like maybe earnings and schooling. So somebody goes to school, does that improve their earnings? Earnings would be the outcome variable in that case. Going to school or not going to school would be the binary categorical regressor. And if this estimation is, we're basically trying to find the treatment effect. And that language comes from basically the medical industry. I give a patient a treatment and then I want to know the effect of that treatment. So now that has been adopted in the policy world and in all types of econometric estimation. We're going to treat somebody with a policy or treat somebody with some type of variable, and then we're going to see what the effect of that was. In general, when we're thinking in those contexts, we refer to it as a treatment effect. So some economic examples, and even broader than economic examples, might be the impact of price gouging regulation on online searches for hand sanitizer during a pandemic. So I use that example because I have research about that example. So that's an example of a treatment effect. Price gouging regulation, we could think of that. Sometimes it's not a 0-1 binary, but it can be. In some contexts, it is. Do they have it? Yes. 1. No. 0. So that's why that might align with that categorical binary variable. The impact of a master's degree on lifetime earnings. So oftentimes people go to get graduate degrees and they want to know what's going to be the impact of that on my lifetime earnings. Model a statistical analysis that's trying to estimate that number would fall under treatment effect estimation. What is the effect of being treated with a master's degree? Now, right away, what's going to be interesting about that is individuals select in to being in master's degree programs. We don't randomly assign this random person will go to a master's degree, this person won't. And it turns out that those people that choose to get master's degrees probably already have characteristics that lead to higher lifetime earnings. So that's going to be the fundamental problem, selection bias in estimating treatment effects. There can be other problems too, like endogeneity. In fact, selection bias is an example of endogeneity, which I mentioned in the last lecture. But this selection bias issue really lives inside of this treatment estimate stuff because it comes up so much. Because A, there's so many questions that are like, I want to estimate a treatment effect. And B, because sample selection shows up so much in those types of research questions. So that's why this is sort of a separate thing, although tons of it aligns with issues of endogeneity. Okay, so the impact of a new tariff on electric cars produced outside the US on the retail price of electric cars in the US. So when I was doing this, a big new tariff came on electric cars. That would be an example. We treated the electric car market with a new tariff, and now we want to know the outcome. So the price would be one outcome we might be interested in. How did that impact the prices? So one huge place that econometrics and economics deviates from other sort of data analysis type disciplines is a focus on theory. And I think this is really important. Oftentimes, people, other types of data science, oftentimes hate theory. They think it's not useful anymore because we have huge computers. If you ask me, if we look at current data about job market outcomes, for example, and we see, man, computer scientists are struggling in the job market. Honestly, I think one thing that leads to that is the abandonment of economic, and not just economic, the abandonment of theory in general. So a lot of times new stuff is like, I have so much data and so much computing power that the computing power and the data will tell me everything I need to know. I think that's a huge mistake. I think we've already seen that in this class. On our very first lecture, we saw that having more data was not useful in getting the answer that we desired. And I think nowadays we're finding that because now we have so much computing power and so much data, it seems like theory shouldn't matter at all anymore, if that's true. What I find in my consulting work, for example, is probably my clients pay me more for theory than for data analysis. Fundamentally, I think that's because the supply of data analysis is much larger than the supply of people who can rigorously think about theory. Now, they definitely want me to marry my theory to data analysis, but that's honestly the easy part. Why? Because we have super powerful computers that on it can do so much data analysis for us that I think, and they tend to be pretty bad at theory, actually. Like AI is not necessarily great at theory. It's good at simple theories, it's good at brainstorming about theory, but it is not as good as theory as it's just like, hey, run me a regression, run me a two-stage least squares regression. It's really good at those because those are algorithmic questions. It says go find, it's like go find the instructions for a two-stage least squares regression in your memory and then apply those instructions. Theory is not really like that because theory often involves more things like art, honestly. We have to be very creative with our thinking about the application of theory and coming up with new theories that are rigorous. So hopefully that was somewhat motivating to this sentence. One of the most important tools used to get at this idea of causality, did something cause something else, developed over thousands of years of humans reasoning, is the application of deductive reasoning by grounding empirical research, data analysis, using data to generate information and knowledge. That's what empirical research is in theory. So we want to ground that in rigorous theory. At least that's my claim at the beginning of this lecture. So we're going to use this idea of having a theory on this price gouging idea really quick. So imagine here's our hand sanitizer market. We have a downward sloping demand curve for hand sanitizer. This is before a pandemic occurs. And then all of a sudden a pandemic occurs, and what we'd expect is a right and outward shift in demand for hand sanitizer. This means that for any given quantity of hand sanitizer, demanders would have paid more, or for a fixed hand sanitizer price, they would have bought more. So that's the definition of an outward shift in demand. We all kind of saw that happen during the pandemic. Now, another thing that happened during a pandemic and happens during many emergency situations in the United States is that we have price regulation. So price gouging regulation specifically, usually that how that works is something like you can't increase the price more than 5 or 10% from what it was before the emergency. These regulations usually live in emergency declarations. And then the governor declares an emergency. And when the governor declares that emergency, that turns on price gouging regulation. And usually the text is something like you can't increase prices 5% or 10%, and then they apply to certain products. Like in the pandemic, they applied to hand sanitizer. During hurricanes, they apply to gasoline in Louisiana, things like this. So in economics, what this does is, so this black line basically says the price cannot go above here. Now, importantly, we have a post-pandemic market price that's higher than the price regulation. That's going to lead to economic issues in this example, theoretically. So here at this new equilibrium in our new demand curve and same supply curve. We assume that supply didn't change in this environment, although it could have, and that would be important to think about. So here we have the price regulation line. Well, the quantity supplied is down here at about 20. The quantity demanded is above 25, maybe 27 or 28. So that means the quantity demanded is higher than the quantity supplied at that point. That's what we call an economic shortage. So my co-author and I actually did this project, and we looked at Google Trends data, and we showed that in states that had regulations like this, we observed more Google shopping searches for hand sanitizer. So that was our outcome variable that we found of interest. Our theory being, if you have a shortage, and there's a lot of economic research on this, people go and search for goods that are in shortage, and we have previous evidence of that. So we thought, well, one place that we search nowadays that we didn't search so much in the past is on the internet, and Google is nice enough to collect some of that data for us. And in fact, we did show and rejected the null hypothesis, as they say, that this wasn't occurring. And we saw a statistically significant increase in hand sanitizer online searches in states that had price gouging regulation. Now, and we used very hardcore econometric tools to sort of back up this theory. But when I talk to people about this paper, I always emphasize the theory because this theory is rigorous and it's a simple story. It just so happens that the empirical results are consistent with this story, but how can we make the causal claim? Where does the causal evidence live? My argument is the strongest evidence that we have that price gouging regulation caused more searches is the theoretical evidence that I've presented here. Yes, we have empirical evidence, data to back that up now, but my claim is that this is the strongest evidence that that occurred. Not everybody would agree with that claim. So it's my claim and it's my opinion, but I want you to at least critically think about the possibility that theory does still matter. Also, just really quickly, in the terms of generating ideas, even to make any type of connection between price gouging regulation, searches for hand sanitizer, I kind of needed this theory to rigorously tell that story, to even get there to the potentiality of causality. Maybe nobody believes this theory on the causality and emphasizes the empirical strategies like two-stage least squares, or having a real well-designed natural experiment. They may believe that more, but even getting there, even my ability to use those techniques demanded that I have some knowledge about these theories. So now let's get into actually estimating treatment effects like this. So generally we focus on what's called average treatment effects. So obviously that's what this sentence says. So let's look at a simple example of that. Suppose we are interested in measuring the impact of a master's degree on lifetime earnings. Let Y, so that's going to be lifetime earnings, 1I denote the lifetime's earnings of an individual I if they earned a master's degree. So this 1 means yes, they earned a master's degree. And let Y0I, this 0 means they didn't earn a master's degree, denote their lifetime. So the same person, their lifetime earnings without earning a master's degree. So now we're imagining two versions of a person, right? Because that's how we'd fundamentally, in theory, that's the true difference. Is I watch that same individual go through life with and without a master's degree. And then if I could actually observe both versions of that human being, that would be a good estimate. However, obviously we can't observe both versions of a human being. So let TI now be a categorical variable saying that's a 0 or 1. It's a 1 if they go to a master's degree and 0 if they don't. And then we can write YI for any individual is their earnings without a master's degree plus whether they got one or not multiplied by the differential earnings between the two. So if T is 1, then their lifetime earnings is what they earned without a degree plus what they earned sorry, it's minus that, and then we just get y1i in this situation then. So the y zeros go away when t is 1. We could only make observation on average impacts of master's degrees across individuals because we can never observe this for one individual, right? Because they'll either have a master's degree or not. So we can try to get at the expected value of this number over many individuals. We can never get it for one. And then we often also think about the average treatment effect on the treated. This could be true because there could be heterogeneous treatment effects. It could be that the effect on the people who got master's degrees is different than the effect if we forced everybody to get a master's degree. That's probably true because of selection. Not everybody might have the same return from a master's degree. And in particular, the return of people who got master's degrees might be different than the return that people who didn't get master's degrees. That's a little bit different than sample selection bias, though, which is worth thinking about. So this isn't really a claim about bias. This is a claim about the potential for heterogeneous, different treatment effects across individuals. In particular, the treatment effect could be different for the people who got master's degrees than it would have been for the people who didn't get master's degrees. So we can't necessarily say, if we're dealing with this number, we can't say like, oh yeah, if you applied the treatment to those other people who didn't get them, then they'd have the same return. Writing this way explicitly, we're just explicitly acknowledging that might not be true. So we can highlight what's called the counterfactual nature of estimating treatment effects by this rearrangement. So if we write these given t equals 1, that equals the average given t equals 1 minus the average given t equals 1. But notice this is the average of not having a master's degree, given that you have a master's degree. So what does that even mean? That means that we have to make an estimate of something that's totally unobservable. What would have had happened to this individual had they not gotten a master's degree? We actually never observe this data. That's the counterfactual. So something that did not in fact happen, but we need to imagine what would have happened to make essentially this comparison, which encompasses our estimate of what happened to them because they got a master's degree. So selection bias, as I mentioned, is really the big issue that shows up here. A major focus of econometrics is in the context of treatment effects is the problem of selection bias. There may be factors that influence the outcome of interest that also influence the probability, is what this should say, of being treated. So it could be that those people who have higher earnings potential already are also have a higher probability of earning a master's degree. That's probably true in a lot of cases. So in other words, the probability of them being in the treatment group and the control group is not the same. In an experiment, we'd flip a coin and say, you're in the treatment group, you're in the control group. That is not how selection into master's degrees or PhDs or a lot of different types of treatments where we're just observing. A project in your class right now where this is definitely an issue. Selection into different types of math classes, because we might want to know what is the effect of online education. And there's a lot of econometrics research coming out about that right now that tries to use things like natural experiments or random variation in placement into those classes to avoid selection bias. So for example, at West Point, a military academy, students don't just pick what class they're going to be in. And an economist that worked at West Point convinced the administration to randomly put students into some online classes and face-to-face classes and randomize instructors over those, because that's another thing you'd have to think about. This is the type of thing that econometricians are trying to do to solve these issues. Because if you're just watching students sign up for online or face-to-face classes, then that's probably not happening randomly. They're selecting into those for a reason. And that reason might be correlated with outcomes in those classes. So that's fundamentally the issue that we have to think about with anything like that. So, for example, there may be factors that influence the probability that someone will get a master's degree, clearly, that are also correlated with lifetime earnings. So, if somebody who is smarter is more likely to get a master's degree, being smarter is probably correlated with higher lifetime earnings. And so, those are going to be mixed together in any simple treatment of that data. So the and that's going to be omitted variable basically, unless you have some type of measurement. So we could try to control for selection bias if we have a lot of data, but that's oftentimes an issue. We can't control for everything like ability. This omitted variable problem that will arise if we simply compare average salaries across individuals with and without master's degree can be made explicit by noting. So here we go. Now we don't really know which ones they are, right? So we're not putting the ones and zeros on the Y's. So now we're just saying, okay, this person who had a master's degree, the average of people with masters minus the average of people without masters. Okay, now we can substitute these in because in our data, those people are the people that got the masters or didn't get the masters, conditional on the treatment, variable. And now we can break these down. So this is recombining them right here. We have y, the difference in the people's salaries given t equals 1. This is something we don't observe because we don't have this difference over only t equals 1. And then plus these two parameters, where the first term in the last line, so this is the average treatment effect on the treated, and the second term in brackets, so all this is the bias resulting from the fact that earnings of individuals without master's degrees, this may not be a measure of what the earnings of master's degree holders would have been had they not earned their master's degrees. So this right here. So we're basically using this guy as a stand-in for this guy, but maybe those aren't the same number. Okay. So by using this as a stand-in for this, we might be introducing bias. And that's worth thinking about. Make sure that you can see that this reflects the selection bias story that I'm telling. Like that's something you probably need to stop and think about. Note that if expected income is independent of receiving treatment, as opposed to being independent of the treatment itself. So let's really carefully think about what that even says. If expected income is independent of receiving the treatment, as opposed to being independent of the treatment itself, then there is no bias. So such independence might be achieved via random assignment. So receiving treatment, that's like saying if we randomly give you master's degrees and then we observe that you do have higher income as a result, then that would be a scenario like this. So the income is not independent of the master's degree if I observe a difference, but giving you a master's degree was independent of your income potential. So that's what we kind of want. If we can argue that this is occurring, then we can argue this number we've estimated is actually the treatment effect. Such independence might be achieved via random assignment. So like flip a coin, make somebody go to a master's degree if they have a heads, and then don't let them get a master's degree if they have tails. We can imagine that being really bad and important questions of policy, like what's the impact of smoking on lung cancer? Okay, we'll just flip a coin, and if they get heads, we force them to smoke. And if they get tails, we don't allow them to smoke. So that's obviously going to be an unethical experiment. Those are sort of some of the areas where a demand for these types of techniques came from, because that's an extremely important question of public policy and a business question maybe too for insurance companies. But we can't ethically do an experiment on that problem. Similarly, drinking alcohol on pregnancy, and I think that actually conversation came up with one student because that's a very famous sort of econometric exercise where somebody figured out of mystery and data. So there was many years of studies showing that in Europe, when someone was pregnant and drank small amounts of wine, that had no impact on the fetal health of the baby. However, in the US, when they had exactly the same dosage of alcohol, so a glass of wine a day or something like that, or 2 glasses a week, those amounts didn't have effects in Europe, but they had large effects and negative effects in the United States. That basically, economists showed that was a selection bias problem because people selecting into drinking wine in Europe are fundamentally different than people who select into drinking wine during pregnancy in the United States. So, strategies to estimating treatment effects and observational data. So, observational data is like data. We could go collect data from surveys on people who smoke, for example, but we can't randomly assign them to smoking. So that's observational data. We can go out and observe in the world people who smoke and people who don't smoke, but we don't have random assignment. And then what the problem is that the choice to smoke may also influence health. That might be correlated with other behaviors that influence health, which I could avoid if I could randomly assign people to smoking. But that's obviously unethical. So we need to think of techniques where we can just observe that some people smoke and some people don't, but we still want to get at treatment effects. What is the effect of smoking? So observational data is data that was produced via random assignment, was not produced via random assignment of treatment. And our goal is to estimate a causal treatment effect from such data. First, we assume a constant effects model, i.e., that the true effect of treatment is constant, or the difference in these two numbers, one of these at least is unobservable, right? Is alpha. So we're just going to assume that. This is not a necessary assumption to estimate treatment effects using regression, but helps us understand the modeling and associated assumptions. So we don't need this assumption. It's just simpler to think about what's going on with treatment effects when we make that assumption. And so, like in the context of our master's degree, this is like every single person who gets a master's degree has the same true treatment effect. They may not have the same difference in lifetime earnings because there's other things going on that we're going to try to figure out how to control for right now. But the treatment, the effect of the master's degree is the same. We assume that only variables that are correlated with both T being treated and Y, the outcome, so like whether you got a master's and income, the outcome of interest, are observable and are collected in Xi. So we assume that only the variables that are correlated with both of these, the outcome of interest and the outcome of interest and the treatment, whether being treated, are collected in a variable, in or X matrix, or independent variable matrix. These are the variables that would cause omitted variable bias if they were missing from this model. So that's why we're describing them in that way. And we discussed missing variable bias in a little bit of detail last time. The assumption that allows causal interpretation of treatment effects, estimating using regression, is the expected value of earnings given X and TI equals X beta. So this is base X prime beta. So this is us applying our population coefficients to our data, and that's going to give us the correct expected value of Y. This expression says that the expected outcome of an untreated individual is independent of their treatment status given X. Or once we control for X, right here, outcome of individuals in the untreated subpopulation is independent of the fact that they are in the untreated subpopulation. So notice T isn't here. Xi beta is all that's here. So it doesn't matter what happened with T. We have the correct expected value from our regression on Xi, those variables described in this way, the ones that are correlated with treatment and outcome. So if we have that, then we can estimate the treatment in an unbiased and consistent way. Since we assume the treatment effect is constant, this also implies that the outcome of individuals in the treated subpopulation is independent of treatment status given xi. So this, because of that, that's just a constant. This assumption leads to a similar statement about those who are treated in the population. For example, individuals who earn master's degrees probably have higher GRE scores on average than individuals who do not earn master's degrees. High GRE scores are likely positively related to lifetime earnings. So that's an example of a variable that both leads to treatment and leads to higher earnings. This means that expected earnings are higher in the subpopulation of individuals with master's degrees. The question is, after we control for GRE score, are expected incomes the same on average in each group? So the people that select in but don't get, so we want to know like what their earnings would have been if they did select in but didn't get a master's degree versus didn't select in and didn't get a master's degree. Now those averages should be the same once we control for GRE score. But we never observed the I selected into a master's degree and didn't get a master's degree because that's not observable. So whether we've done this or not is not observable. So what might we claim to try to say, no, we're okay? Well, one thing that we can come up with empirical evidence of that, but another thing is going to theory, going to the theoretical underpinnings of the problem. So the first type of model that is a wide range of models, and I'm just going to show you a very basic version, but like we can add control variables to this and thing. So the above reasoning motivates the question, which of variables should be included in xi? Broadly speaking, we might observe variation over time and across space, yi, or both, yit. So yt, that would be across time. Across space, yi, or both would be yit. For this class of models called difference and differences, we're going to need to assume that we're observing over panel data, which is yit. This is time series data. This is cross-sectional data. This is called panel or longitudinal data. So let's simulate some data for master's degree model to help understand this issue further. So we might have something like this, where we have a control group of people who never got a master's degree, and these are their lifetime earnings over time or their income over time. And then we have a treatment group. These are the people who got a master's degree, and then maybe they all got a master's degree at the same time. We could probably set that up in our data to make it so we only looked at a certain class of people and then track them over time. So this chart would strongly sort of support the use of difference and differences and the fact that this distance right here, the average distance between this dot and this dot's vertically, is our treatment effect. Why? Well, we observe that over time, they had parallel trends. So it looked like these things were changing. Although they were already different, that could be things like people who get master's degree have higher ability. So they were already earning more. And then this extra bump, can we attribute that extra bump to earning a master's degree? That's a question. That's the question. This type of chart would be strong evidence of that because of the parallel nature on these lines. The fundamental assumption is would this green line have just remained parallel to this blue set of, like if we just draw a line through that, does that remain parallel to the blue one in the absence of treatment? If the answer to that is yes, then we have a good estimate of the treatment effect. We don't know the answer to that because these missing pieces right here, those are the counterfactual data points of these people without a master's degree. We have to make assumptions about what would have happened. So now let's think about different ways we might use these types of data that are often proposed, often alluded to. So in things like opinion pieces and editorials, we oftentimes will see people use time series data and cross-sectional data to make claims about causality. And we're going to see why those could kind of be messed up in this context. So let's say the true treatment effect is 20. So that's what I just coded in. The average difference between this dot and this dot is 20. So treatment before and after. And that basically is going to be, we're going to see how we get that pretty soon. So we coded that in though. So the 20 is the true difference in across. So this number essentially minus what this number would have been. So it's not just minus any of these red dots. What we're subtracting from this number is right about here because it's the average of what we think would have happened. So you have to imagine this line still going up in a parallel way. What's the average of that line? Maybe it's right here somewhere. That distance is going to be the true treatment effect in this context. Because why? Well, it controls for the fact that there was already a pre-existing difference right here. Okay. And it also controls for the fact that incomes on average were already increasing in the data. Those are the two sources of variation that are problematic to this estimate. So let's see what would happen if we use a commonly used but oftentimes invalid time series estimate. We might say, well, I have data on the people who got master's degrees, so I'll just take the average before, or sorry, the average after they have master's degrees, which is right here. That's 113.83. And then I might subtract the average before. I'm just looking at variation over time within the master's degree group. That gives me too big of an estimate, 29, almost 30. What that estimate ignores is that salaries were already increasing over time, and I'm attributing that increase over time to master's degrees, which I shouldn't be doing because we can see down here already no master's degrees are happening, but salaries are increasing. That leads me to a biased estimate of the influence of the master's degree on earnings. Now, another often used but invalid estimate in this case would be a cross-sectional one. I'll just compare the people who have master's degrees to the people who don't have master's degrees. So that's this number minus this number. That's way too big. That's 40. That's basically double what I coded in. What that is ignoring is the fact, look over here. People who decided to earn master's degrees later already had higher salaries. I'm attributing that difference to master's degrees when I just compare these points. And that's why I'm getting too big of an estimate in this case. So both just looking at time or just looking at space will lead to bias estimates. They don't always have to be upward bias. They're upward bias in this case because going up over time, that's why time series is biased. Pre-existing difference, that is positive. That's why cross-sectional is upward bias. We could have decreasing outcome variable over time. We could have the control group being higher in the variable over time. So there's all types of potential for bias in this context. I just use both of them are leading to upward bias in this case. So now you might say, I'm never going to use any of these techniques, but right now, I want you to be extremely skeptical for the rest of your life. You have to A, recognize, is this a time series or a cross-sectional estimate that this claim is about? Are there pre-existing differences or pre-existing trends that are going to mess up these estimates? Because we can actually guess, if I know that this is increasing over time, I can guess the bias of this estimate. If I know that the pre-existing difference is positive or negative, I can guess the bias in this estimate. So note that we could fix the bias in the time series estimate if we controlled for the growth rate and income over time. So notice this is too high because I'm ignoring my TS estimate right here is too high because I'm ignoring the fact that salaries are increasing. Well, look, I actually have a parallel trend. I actually have information about salaries changing over time that is not inside my treatment group. So if I think that the control group is increasing at a rate similar to the treatment group, then I could actually control for that. I could say, well, if this growth rate is consistent with this growth rate, then I could use this growth rate as an estimate. And I could say, okay, I'm just going to put this growth rate right here in the control group. I'm actually going to look at the post control change because maybe this isn't linear. Maybe this goes crazy. But if I observe it in the control group, I could take that trend and I could put it up here on my treatment group one and say, assume that the treatment group would have evolved the same way as the control group. If I have strong reason to believe that, maybe from theory, by the way, or maybe from other empirical evidence, like the evidence in the pre-group, in the pre-time period, then I could subtract off that time change, and then that would get rid of the bias for me. So let's take a look at that. So in the time series estimate, I have, this is my original time series estimate. So what the treated group looked like after master's degrees minus what they look like before master's, we saw that that's too big because of changes over time. Well, I can also observe what happened to the control group. So this is what happened to those didn't get a master's degree minus them over time. Now, if I subtract that change off, then I have my change in my treatment group subtracting the control in the change group. So in my treatment group, I have this dot minus this dot, but that's probably too big because notice, and even in the control group, this dot is higher than this dot. But if I subtract this difference, so this vertical difference between these two off of this vertical difference, then I've controlled for the change in time that was unrelated to the master's degrees. And look at that, I get an estimate that's close to my 20. I built random variation into this, so that's why we're not getting exactly 20. Now, the cross-sectional estimate is biased because there was a pre-existing difference. Well, what if I took this distance, which leads to the way too big 40, but then subtracted off the pre-existing difference? Boom, I get exactly the 19.5, because what's really cool about this is that this and this are just algebraic rearrangements of one another. So these equations are exactly the same. So, and these equations are both through the same, and that same equation is the difference in differences estimator right here. So, and I'm going to actually have you show the regression version of this difference and difference. I'm going to show you the regression differences estimator, and I'm going to ask you to show that leads, because again, this and this are algebraically the same number. Now what I want you to do is we're going to look at the regression right now. In your homework, you're going to have to show that this regression down here leads to fundamentally what these equations look like. So just note that those are the same. So that's what I've been saying verbally to you, that these are the same. They're just algebraic rearrangements. And both of these are just, these adjusted estimators provide unbiased estimators. These estimators are both simple versions of what's called the difference in differences estimator, which will provide unbiased estimates of treatment effects if the change in the outcome variable in the control group over the treatment period reflects what the change in the treatment group would have been like in the absence of treatment. So let's look at the graph. That's just restating the assumption we're making is that these green lines that are forming an obvious linear trend in my simple example would have evolved after this point at this rate. So we can literally take these, shift them up here to be aligned with these. That's the assumption we're making. And then the difference between this dot and this shifted up dot is the correct treatment effect. Both of these pieces of algebra that I showed you lead to that same calculation of the distance I was just showing you. But this is fundamentally the assumption we're making. And this often comes to a story. So if you're doing this on your poster, usually you have to make some type of a story. Look, it makes sense that these would have evolved the same way as those. Random assignment will lead this assumption probably to hold in the data. So the change in the outcome variable in the control group over the treatment period, we observe that. That reflects what the change would have been in the treatment group in the absence of treatment. We do not observe that. That's the assumption we're making, though. The most common way to assess this assumption is via visual inspection of the pretreatment trend. So we look at this graph and we say, yeah, those are very close to parallel. So I'm willing to make the assumption that they would have been parallel. They are still parallel, just shifted up. I'm assuming that that would have been parallel in the absence of treatment. That's the assumption we're making here, but we don't observe that part. We're using this information over here to claim, yeah, they're probably still parallel. And we could do that in much crazier time series looking data. It doesn't only happen with like very straight lines. So oftentimes in these presentations, we'll see crazy volatility in both groups, but it matches. And then you say, look, those things are evolving at very similar trends. So now I'm more willing. That's evidence that this parallel trends assumption, which was what it's called, is holding. The TS and the CS estimates show that the DID estimator controls for variation in time and variation in space between individuals. So that's what variation in space in this context of master's degrees would mean, without directly observing the specific variables that influence that change, because there could be many and some maybe we can't collect data on. So that's what's really nice about this estimator. Note that panel data is required for this estimator. We need to observe variation across space and across time for this to work in both treatment and control groups. The difference in differences estimator will fix selection bias as long as treatment status is independent after controlling for time and space variation in this manner. This will be true if all such variation is 1, time invariant within groups. So there has to be the differences between the treatment and control groups. That difference has to be invariant over time. Is a kind of a simple way to say what that is. This is another point you need to stop and think about 1 and 2 right here. But a simple example would be the difference between the control and the treatment group doesn't vary over time for reasons other than treatment, is what I should say. Because we expect the master's degree to change the difference in those groups. But if something else is causing the difference in those groups to change over time, that will be an issue for this assumption. That will violate the parallel trends. Variation 2, variation stemming from time impacts the groups equally. So if something other thing, maybe all of a sudden the government sends checks to everybody and everybody's income goes up in the post period, as long as that effect is the same in the control and treatment group, we're fine. But it has to be the same. If something differentially affects them over time, that will be an issue. In our simulation, the average difference between treatment and control is constant, absent the treatment effect satisfying 1, and the rate of change in incomes is equal in the 2 groups satisfying 2. The difference in differences will lead to biased estimates if there are time and space varying variables that impact both outcome and treatment status that are missing from the regression. For example, if all of the master's degrees earners also participated in a job training program, but none of the controls did, that's basically another treatment that occurred, then that would still lead to missing variable bias. Why? Because that new variable was different across groups and across time. So we're not controlling it for it. It's not time invariant, and it's differential across the groups. So this is going to be an issue. Now, what's nice is that we can do a regression version of the difference in differences estimator, and then we can add whatever controls groups for that. So as long as we can control for the job training program somehow, then we'll be able to fix this issue. Now, in the way I've described it, all of the master's earners did it and all of the control didn't do it. We actually couldn't control for that because we don't have the necessary variation. Getting a master's degree and getting the job training are perfectly linearly related in this example, that violates a different assumption from regression. However, we can imagine, like, what if 90% of the master's people did the job training and only 10% of the control did? That will lead to different averages. Now we can control for it if we have a big enough data set to estimate the impact of the job training separately and control for it. So that's kind of why we want, instead of this just algebraic work on the sample averages, that's what this is, right? Sample average of Y conditional on this, sample average Y conditional on this. That's just algebra on the sample averages. Well, we can do a regression version of this, which is mathematically the same, which you will show is mathematically the same. So the regression version of this is YIT equals an intercept plus beta 1 times treatment group. Treatment group equals 1 if you're in the group of people who ever gets a master's degree. So this is always 1 if you're in the treatment group, even before you have the master's degree. Post-treatment, this is always 1 for everyone after this line. So no matter what group you're in, this variable post-treatment will equal 1 if the time period is greater than the time period when master's degree occurred. So this is 1 for everybody that's green, no matter where you are in the sample. So you have that variable is 1 in time period 2. Post-treatment is 0 in time period 2. Post-treatment is 1 no matter who you are in the post-treatment period. Because that treatment group variable is controlling for all of the differences across space. Post-treatment is controlling for all differences across time. And then we multiply those two together. Now, what's going to happen with this one? If this will only be 1 if you're in the treatment group and you're in the post-treatment period. That's what's netting out specifically this data. And so that's on the beta DID. I labeled that beta DID because that population parameter is the treatment effect in this setup. So what we want to do is find a way to estimate this regression unbiasedly, consistently. And if we are able to do that, then our estimate of beta DID will be our estimate of the treatment effect, and it will be unbiased under the assumptions we've made so far. So what you will want to do on your homework, by the way, is prove to me that this simple version of the DID regression is the same as these up here. That'll amount to you saying, like, okay, B naught, the estimate of the intercept, what does that number represent? It represents an average, a sample average is what just B naught will be. Because you can imagine that YIT equals beta naught. If this is 0 and this is 0 and this is 0, then all of these will cancel out and Y will equal B naught or beta naught. In the sample B naught, in the population beta naught, what is the meaning of that number? You should be able to just think that number has a very simple meaning. Now that's the simpler version of beta of a difference in differences. And now what if we have many control groups, treatment at many different time periods and things like that? So sort of what this has evolved into is called the two-way fixed effects difference in differences estimator. So we have our same outcome variable, but now we have alpha I. So maybe we have 50 states and 20 of them are treated and they're all treated at different time periods. Well, we can give every single state its own intercept. I individuals in this data, a state would be I, because that's maybe where we're collecting the unit, the geographic unit we're collecting data on. If we write this way, basically what we're saying is we're allowing our intercept alpha to vary over I. So I'm going to give every single state its own intercept. What is that going to do? It's going to control for differences across states in income that have nothing to do with treatment, that are pre-existing. I'm giving every single state its own intercept. That's going to allow the line to shift up and down based on the averages in the state. So by giving every state its own intercept, I'm controlling for pre-existing differences, even between treatment and control states. But because I'm doing it for every state, I'm controlling specifically for between treatment and control states. I'm doing that even more granularly because I'm also controlling for differences between treatment states beforehand. So I'm getting more granular, but encompassed in controlling for the difference between every state, I must be controlling for the difference between treatment and control states because those are examples of individual states. Gamma T. Now up here, we said we got to control for whether we're in the pre-treatment or the post-treatment period. Well, what if we're getting treatment at different times for different states? I could just control for the difference in every single period in my data. So I say I have state level. So now every state has its own intercept term, and I have 10 years of data, 2000 through 2010. I have a dummy variable in my data called 2000. Did this observation occur in 2000? If yes, then there's a 1 here. If no, there's a 0. I give every single year its own dummy variable, basically. And this essentially gives every state its own categorical variable. So I'm controlling for all differences between states. And at the same time, I'm controlling for all differences between every year. Encompassed in controlling for all differences between every year is controlling for differences between before treatment and after treatment. Now, I'm controlling for every year, even if they're both pre-treatment or both post-treatment. But by doing that for every year, I must also be controlling for differences between pre and post years. So this is just more granularly doing these control variables. Now, of course, I have one special variable called treatment active. That's only equal to 1 if a state is experiencing treatment and is in its post-treatment period. Otherwise, it's 0. So that is the analog to this variable right here. We have to be in this situation in the master's degree group after master's degrees for this variable to be 1. That is our key variable of interest. Beta DID right there is our key parameter of interest. And then I've just said, oh, by the way, anything that is not time invariant or invariant across space, if we can get data on that, that's going to be an issue for us. If it's correlated with both this and this, that's going to cause missing variable bias. What's nice about the regression version of DID is now we can pack in all of those control variables to the extent we can get our hands on them. So this is a very common nowadays regression setup because there's a lot of treatment effect estimation happening. And so this is like the base model that basically everybody's using if they're trying to do treatment effect estimates. And then they're going down the rabbit hole with adding new techniques to this model. So I think I told you everything there. So an example, the one that I mentioned above that I motivated with theory. So a co-investigator and I used two-way fixed effects difference and differences regression to estimate the impact of price gouging regulation on social context. So up there, I said on hand sanitizer searches, but we were also able to get data on Google mobility, which was pretty cool because it told us social contacts. Like if 2 people walked by each other in a grocery store or a pharmacy, we had data on that. So now we want to know, do people have more social contacts as a result of price gouging regulation? Because if they do, that would obviously be interesting from a policy standpoint. If our goal is meet people not making contacts in public spaces because there's a pandemic, we'd want to know if other regulations like price gouging regulation were influencing that. And we did in fact find that price gouging regulation increased social contacts because people were doing the same thing. Instead of searching online for hand sanitizer, they were searching in stores and Walgreens and places like that to find hand sanitizer. And we showed in this analysis, we explained that theoretically using supply and demand. And just humans. What do humans do? If there's no toilet paper left in the grocery store, they go look at another grocery store. That is a simple theory that happens to be true. So we have our state level intercepts here. We ultimately use county level data. So every county, 2,000 counties, we had a lot of data because we had like daily data for every county. So every county got its own intercept. Every day got its own intercept. That's the analog of alpha I here and gamma I T here. I'm using both alphas because it's okay. We can be fast and loose with notification because alpha I is that control for individuals. For us, that's counties. Alpha D is that control days. So I'm just labeling it by D to be clear about it in the paper. Then we just call this beta to be like the beta, the big one is what we want. Beta is going to be our treatment effect estimate. Law equals 1 if a state ever has a law, but then we're multiplying that by whether there was an emergency action taking place. Because like I said before, the governor declaring emergency turns on the price gouging regulation. So all of these states and counties have price regulation on the books, but it is activated when the governor declares an emergency. So the multiplication of these two variables gives us our treatment, because some of the places activate an emergency, most places activate an emergency, but not all of them have laws. So this gives us the treatment group times post-treatment variable that we are interested in. So this is our treatment effect estimate of interest. And then this is a sort of a special control variable that we thought was important. What happens to social, like maybe that you don't have a price gouging law, but the governor does declare an emergency, which was common. That probably interacts then with population density, because if that happens in a state like North Dakota where there's no other people, you're probably like, whatever, I don't see any other people ever anyway, so I have very low risk of getting COVID. So we'd expect people's behavior to interact both with how dense their community is and with whether an emergency was activated. So this, from theory, we designed this very special control variable, and we separated out from our general list of controls, which include things like rate of COVID before the price gouging took place, other types of things. Things also like political variables were there too. Those were less special to us. We put a lot of work and discussion into this one, theoretical discussion. So that's often why we separate it out, because we want to discuss it in more detail in the paper. So this explains what I was just saying there. You can take a look at that paper here at this link if you'd like to. But actually, I'd like to show you a couple other papers that I included. If you go to modules, so right now, we've been talking basically about what's called causal inference, both in endogeneity and instrumental variables and in treatment effects part 1. We're going to revisit both of these things later in our next lesson, simultaneity, OLS and 2LS again, and then treatment effects part 2. But what I wanted to show you now is I've added a couple papers. One, this was my teacher that taught me a lot of the stuff that I'm teaching you guys, called this the Bible of econometrics. It's a pretty old paper. It's 1992, but these two are maybe two of like the most leading researchers in what's called causal inference, thinking a lot about this stuff like endogeneity, treatment effects. These are two of the biggest people that have ever worked on that. And this, estimating the payoff to schooling using the Vietnam era draft lottery, is one of the most famous papers in that. And so they do a lot of theoretical reasoning at first. And their goal is to estimate the earnings resulting from schooling. So there's a theory: if you have more schooling, you have more lifetime earnings. But people who have more lifetime earnings potential select into schooling. So they discover basically a natural experiment when they see that the Vietnam era draft lottery, people essentially were randomly selected out of schooling because they were drafted into the Vietnam War. And this is a very famous, I'm not going to go through deeply through the details of it. It's well written and basically easy to follow. And I think I asked you to do a little bit of work on this paper in the homework. So you'll have to look through some of these equations. But this is a very famous and important paper. And I think will be very valuable for you to take at least skim through this paper and look at some of the stuff. So then I put another paper here. So what's cool is this is still people are thinking of a lot about these issues. And this is kind of what's called the causal revolution in economics and econometrics. When people started going down these rabbit holes on causality and the stuff we've been focusing on. This paper that I've uploaded was actually presented in our department, the Department of Economics at Weber State, just the other day. You can see this is a very recent draft, and you can click here to get in even more. If they've edited, they probably haven't edited this since this draft. But I just want to show you, because I know the notation gets complicated. I'm going to show you an example of getting more complicated. But if you use your brain and use the skills you're learning in this class, you can understand very complicated things. And that's fine. So I first just want to talk about their goal in this paper is trying to estimate the treatment effect of having a good teacher. So one of you is doing a project that's estimating like what is the treatment effect of being in an online class. What you're doing is a little bit more complicated than that, but I'll just say it that way. That's very similar to what this is. And the issue is that they're trying to deal with is, well, a motivated student might be looking around more for good teachers than an unmotivated student. So maybe you're not picking up the effect of the teacher at all, but you're picking up the effect of the selection into that teacher. So let's think about this notation really quick. Consider a generic achievement measure A star. So that could be like a GPA test score on a standardized exam or something. And then following the value added literature. So what's the value added to a new teacher? That's what they're saying. So they've looked at other papers trying to estimate this, and they're building off of those other studies. So we express achievement A star IJSCT. So there's a lot of those things there now, obviously, of student I. So that's what the I is, just a student, because they're observing variation across students. So that's the first thing. In course C, so there's a C there, so they might have different courses. Maybe it's a math course or an English course. So they want to index their variable by that. Subject S, so that's the S, during academic period T in instructor J's classroom. So A is student I's score, J's class, that's instructor J's class, in subject S, like math. In course, maybe it's linear algebra is a specific example of a math class. And then T is the time period. So maybe they're doing the spring 2025, fall 2024. That's what T would be. And so if we model this as being XIT captures student I's background characteristics, maybe they have rich parents, and people with rich parents tend to get better test scores. So that would be something included in X. So that's in XI's background. C are characteristics of other students taking class C with Professor J. So maybe there's characteristics of the other students in the class that influence student I's score or outcome in the class. Row C is a course fixed effect. So maybe there's something about like being in class in the morning that leads on average, or people in that course on average earn higher grades. Then that's a fixed effect, like giving every single course its own intercept, kind of like we gave every state its own intercept and every year its own intercept. That's giving every course its own intercept. And so every individual student is not getting their own intercept because we probably don't observe them enough in the data to do that. But every time period, every semester, you could imagine, is getting its own intercept. That's kind of like giving every year its own intercept. And then, of course, there's going to be leftover. This model will not perfectly predict outcomes. So there's going to be an error term. Notice I haven't said anything about a teacher being a good teacher yet, because kind of what they're doing that's kind of cool and fits with everything we've said so far is to really focus on the idea of value added. They're imagining predicting test scores on all of these things and then subtracting actual test scores from those predicted test scores. That's going to lead to their error term, right? And now they're going to say to have a simpler set of parameters to think about, they're going to say this error term can be subdivided into the impact of the teacher on the score, because that's, we never controlled for that. So that's still in the error term. The effect of the teacher lives in this error term. So now we can say, here's a bunch of error terms. Some of them are high and some of them are low. For the high ones, can any of that be explained by having a good teacher? Some of it will be explained by other stuff still, but maybe some of it can be explained by having a good teacher. So they essentially are cleaning out all of these other effects from their data so they can just refocus on this leftover variation, some of which they propose is involved with having a good teacher, some of it not. So I just wanted to show you that in terms of notation. I strongly encourage you, if you're interested in this stuff, this is a great paper. There's some cool techniques in this paper. If you're the student that's working on the effect of something in a classroom, this would be a great paper to think about. You definitely don't need to go as deep down the rabbit hole as these people have done. These are 3 people, probably all of them have PhDs in economics or possibly econometrics or related data science-y disciplines. And they've been working on this paper for many years. So don't think that you need to go this deep. But I wanted to show you, you can understand complicated things. And this is just another way people might express models, but I don't want you to see this and be like, wow, it's beyond me. No, you know all the skills you need to understand exactly this model. It's just a more complicated thing, what we've been doing, and playing with it in a way that makes it made easier to understand for the reader and for the audience you're trying to get to. Now, I wanted to show you one other thing, and then I'll end the video after this. Is they have this very cool forest forecast biasing, and this actually gets a little bit into a more machine learning type technique on inference. So they're kind of like saying, did we do a good job? Because fundamentally, our goal was to estimate what somebody's score would have been and then compare that score across them having a good teacher or a bad teacher. This forecast bias and value added estimate, forecast bias is a really cool technique because a lot of you in our individual conversations, like, can we even test for the existence of some of these things? Not really directly, but this is a very cool forecast bias technique that sort of uses more prediction type techniques that come out of machine learning and tend to be more related to machine learning, but then checking, did we do a good job on our forecast, because that could then tell us, did we do a good job on actually estimating our treatment effects? So I'm not going to go super deep into that there, but if you decide to take a closer look at this paper, then I definitely encourage you to look at this part because that's a very cool and sort of modern technique in econometrics. So please think about all of this in the context of your project and the last 2 lectures. And don't hesitate to reach out to me if you have ideas. I'm down to brainstorm ideas. Maybe you have multiple ideas that we can talk about, which maybe has the clearest path towards a good project. But yeah, I'm flexible in terms of meeting times. It does not have to be during my office hours. I've already met some people on the weekends, late in the evenings. So just reach out and we'll make something work. All right. Bye-bye.